Hello, everyone. This is a presentation about model network exploration. We live in a world of models, where each model is composed of a set of signatures and their respective implementations. In the first case study, long-term trend is a signature, and its corresponding implementations be yes and no. We define model networks as the set of models that share some of their signatures and implementations. Given such model network, the natural thing to do would be to compare different models. There exists a variety of criteria that can be used for model comparison. It could be qualitative, quantitative, or a mix of both. One example would be ELPD. The value of the metric indicates how well the model aligns with our desired conditions. By using such metric, we are trying to find a model that best fits our interest. We will state this task as model search problem. However, there exist some challenges in model search. One is that evaluating the ELPD value could take a long time, up to 20 to 30 minutes. And given the time constraint and a limited computational resource, we can compute ELPD values only a finite number of times. Another challenge is the model network is large due to the sheer number of combinations of different signatures and implementations. So given a model network, we're trying to find a model that best fits our interest. The input of the model search problem has two distinctive elements. One is the model network as previously defined. The other is the evaluation criteria, which could be flexible. But in our research, we deploy ELPD as our metric. The desired output would be a model or a set of models with high ELPD values. Putting all this into a more rigorous formulation, we have the following. Let's define I as the set of model indices in the model network, and M sub k as the index of the model examined in the case iteration. The constraint indicates that each model examined should belong to the model network, and the objective function is the maximum ELPD value among the models examined during the k iterations. The research questions related to this so-called model search problem are as follows. Firstly, given a model network, how can we find the optimal or near optimal model with the highest possible ELPD value under a computational resource constraint? Secondly, given different strategies to conduct model search, what are their pros and cons? For each model network instance, how can we choose an appropriate model search strategy? We provide two streams of model search algorithms. One is the chain-based search algorithm. We define a combinatorial structure called a chain, and we assume that as one goes along the chain, the model complexity increases. Also, it is assumed that as model complexity increases, the ELPD value of the model increases as well. The other stream of model search algorithm would be Bayesian search algorithm. Given a set of models in the network, at each iteration, we randomly draw a model based on a probability distribution. After we compute the ELPD value of the model, we update the probability distribution and repeat this process until we run out of our computational resource. The four algorithms presented are chain apex predator search, chain search dynamic step size, probability, and score-based Bayesian search algorithms. We use greedy algorithm as our benchmark. The first variant of a chain-based search algorithm is called the chain apex predator search algorithm. Given a model network, we try to identify every possible chain in the network. Once one can view a model at the upstream of a chain as a predator. An apex predator is a model that has the highest hierarchy in every chain that contains the model. We filter the entire model network into a set of apex predators, and we only examine them and find our best model. The second variant would be a dynamic step size algorithm. Given a particular chain, we search along the chain while adjusting our step size. We utilize the ELPD values of the previous examined models to determine the step size. The key assumption required is that a linear approximation of ELPD value with respect to chain index is possible in a local neighborhood in a chain. Now we transition from chain-based algorithms to Bayesian search algorithms. There are two reasons behind this transition. One is that the chain structure is too specific. For example, given a model network instance where there is no apparent hierarchy between implementations of each signature, it might be hard to identify a chain of model. Plus, it requires strong assumptions Regarding the relationship between model complexity and ELPD value, the other reason is that in chain-based algorithms, the information gained from each ELPD computation tends to be fairly limited. It's either confined to the examined model itself or to the models in its local neighborhood. Meanwhile, Bayesian search algorithms update the probability distribution over the entire model space. This indicates that these algorithms gain some information about a variety of models at each iteration. So the first variant of the Bayesian model search algorithm is the score-based search algorithm. At each iteration, we first compute the score of implementations. The score of each implementation is defined as the mean ELPD value of the models A, whose ELPD values have been computed at previous iterations, B, that contain that specific implementation. As each model is defined as a combination of several implementations, the score of a model equals the sum of the scores of its implementations. The selection probability of each model is proportional to its score.
It's complicated, but it's really simple. So we talked about how we evaluated a single instance of a model's ELPD, and then what we really want to do is like use that single ELPD evaluation and try to propagate it to as many models as possible. And like if you think about like standard regression, if you do something like group level effects, you need some kind of a common category that's needed, where you can make the assumption that they would tend to share some same traits. Well, it actually turns out that implementations give us a way to kind of categorize type of models with the assumption that, well, perhaps if some models share a common implementation, they might have something together that share a similar trait. So what we do is first we create a probability distribution along the entire model network. So in the example below, so let's say we have 4 models in the network, and then we initialize the distribution to be uniform. So that's a quarter of a probability for each model. And then for the sake of simplicity, I'm going to say that the models number 1 and 4 consist of 3 implementations, and models 2 and 3 consist of 2 implementations. And so what we do at every iteration is we just draw a model according to the distribution that we currently have. In the first iteration, it's going to be uniform, so we just randomly draw a model, and I'm going to call that model sub 1, M sub 1, sorry. And then at the second iteration, we're going to draw another model again. This time, it's also going to be from the uniform distribution, since we haven't modified it yet. And then that's going to be model M sub 2. Now, what we're going to do is we're going to calculate the ELPD values for each of the models. So we would get the ELPD value of M sub 1 and the ELPD value of M sub 2. And then we now actually compare the values. And then let's say that the ELPD value of the model M sub 2 happened to be bigger than the ELPD value of M sub 1. So what we do this time is we take the models that contain the implementation that the model M sub 2 has. So that's going to be A prime. So models 2 and 4. And then we're going to take the probability of models that possess implementation A. That's going to be models 1 and 3. So we take the probability that's allocated to the implementation A, deduct it from the probability distribution, and then we redistribute it back into models that have the implementation A prime. So this works because the LPD value of M2 is bigger than M1. If it's the opposite, then you would do the vice versa. And then we update the distribution as so. And then we would just repeat this process for all implementations and keep doing it until the maximum amount that's allowed for us to do. And of course, when you're actually implementing this, you need to make sure that the updates are not done sequentially for each implementation, because that would mean that a smaller amount of probability is going to be moved in the same iteration. You need to keep track of the amount of probability that's going to be moved, and then deduct it all at the same time once the iteration finishes. So if we actually apply that to the actual model network, this is from the birthday model example. So this is the plot of probability and ELPD. And we've just first ran it up to 5 models. So this shows the probability distribution against the entire model network that we've constructed from 5 ELPD calculations. And then we just repeat this process for more models. So this is 10 models, 15, 20. And then we come up with this really funky discrete probability distribution. This is discrete because the models are, well, discrete. And since we've defined the model distribution to be spanned across the entire model network, what we can do is we can actually get probabilities for models that we don't have the ELPD for. And the ELPD values for models that we haven't evaluated, well, this is for testing purposes. And we're just gonna make sure and see that even for models that we haven't actually calculated ELPD for, we wanna make sure that in general, models that have high probability tend to also have higher ELPD values. And we can see that, we can see a weak relationship between them, and it actually does imply that. And another cool thing that we can do with the model network distribution is we can identify how probability is assigned on a signature by signature basis. So for example, if you're interested in like a specific signature, say day of week trend, and you want to see whether in general the implementation yes or the implementation no works better. And then looking at this plot, it seems that on average, the average ELPD value of implementation yes tend to be higher. So the search algorithm allocated a higher amount of probability to models that contain the implementation yes as to ones that doesn't have it. And then you can kind of see that in general, again, in general it's important. Models that have a higher ELPD value do get higher probability allocated to them. But then this isn't always the case for more kind of sketchy results, because you can see that for uniform and weighted, there isn't that much of an ELPD difference between them. But then the search algorithm kind of gives a different probability to each of the models. This is kind of one of the limitations of our search algorithm, is that I'm going to explain it a little bit in detail later, but it doesn't take into account the absolute values of the ELPDs into consideration. So it kind of views an increment of an ELPD improvement of 1 and an ELPD improvement of 100 exactly the same. It just uses only the proportion of implementations that's present in a model to update the probabilities. And so this leads to kind of the ELPD values and probability mismatching. But then again, you have to kind of take a look at these analysis with a grain of salt, because this only shows the average values of a single signature. So this is always prone to the fallacy of averages, and it does not take into account any interactions between implementations, which is kind of expected in models, right? Because you can expect like some combinations of a link function and likelihood to work better than other ones, and then like some kind of likelihood and prior combination might work better. And this just doesn't take them into account. So what we can do alternatively is we can kind of plot a heat map against the entire implementations. So this shows the average probability allocated to models that contain 2 arbitrary implementations. So for example, you can see that for the implementation yes for the signature days of your hierarchical variance, you can see that in general it works better than the no implementation for all models that contain the yes implementation and some other implementation. And then you can also use this back again to see that this time the implementation no for days of your normal variance works better in most cases as to the implementation yes. But there's kind of a caveat here. It's because if you look at this one, in fact, this model, so a model that contains both the implementation yes for days of your normal variance and the implementation yes for days of your hierarchical variance happens to be the model with the highest ELPD in the entire model network. So you can't really interpret this as like saying, well, since implementation no for days of your normal variance in general tend to work better, I'm gonna completely just disregard any model that contains days of your normal variance yes. That's not gonna work, because this only kind of shows you, well, any type of a distinct relation between implementations that tend to fare well with other implementations. So you can't really interpret this as a way to kind of prune out bad implementations. And we're gonna quickly go over like comparing the results. It's not even a comparison, it's more close to kind of identifying like which algorithms work in which cases and whatnot. So for the birthday problem, the greedy algorithm, I mean, apparently it does find the global optimum, which is 15,384. And then the two search algorithms, chaining-based search algorithms, the A-text search and the step size search, also really show really good results with the small amount of ELPD evaluations. Now, on the first hand, this looks really good, but then if you take a deeper look into it, it's not. The only reason that the chain-based algorithms were able to perform this good is because for this specific birthday model, the models that were at the highest chain, that was at the highest hierarchy, also happened to be the models that have the highest ELPD values. So this is pretty much a perfect setting for the chain algorithm to work. And if it was like a model that was remotely a bit more complex than birthday, or if it wasn't as easy to provide hierarchical information, then you can't really expect the chain-based algorithms to perform this well. And for the Roach model, which is also taken from Aki's case study, you can see that the chain-based algorithms kind of perform worse than the beginning. They can't find the global optimum. This is because it's a bit harder to provide direct hierarchical information about the Roach model as to birthday, because it's not a binary yes or no implementation type of thing. So a really interesting observation is that, like I said before, chain-based algorithms perform in a clearly defined hierarchy is possible, and that's given under an ideal model scenario. But then distributional methods, they can't really find the optimal values in any of the examples. This is the optimal values of distributional models. We just took the mode of distribution. So that might be related to why it can't find the optimal values. But then if we take a look back at the ELPD probability plot, we can see that it provides a group of really highly plausible models. And then if we continue running the iterations, you can see that as we run more iterations, the expectation of the entire probability tends to go up. So it's a really different approach to the standard maximization. It tries to like find a group of models and try to discriminate ones that doesn't. And then it really tries to continuously give little and more probability to models that it finds more plausible. Well, at least in the sense of the ELPD. And of course, our algorithms are not perfect. There's really big limitations to what they could do and what's required for them to work well. And for chains, like I said, they require an ordering of implementations, which in most cases, frankly, they're not easy to find. Like, you can't go and say a normal prior is at a higher order than a Cauchy prior. It's just hierarchy can't be like specified for cases like that. And it also requires an assumption that, in general, models that are at the higher hierarchy tend to be the better performing models. So if this assumption is broken, so if we can believe that the model complexity or the hierarchy has no relation with performance, then the chain algorithm is going to be utterly horrible at finding optimal models, because it's going to completely skip through the other models that potentially might be viable and only look at the models that are horrible. And for the distributional algorithm, the probabilistic variant, like I said before, the matrix's actual values are completely disregarded. So they're only compared within inequality comparison, so whether it improved or not. So that means that the only part that dictates how much probability is incremented or decremented is the amount of implementation that's present in a model. And then you can see that even in the best case scenario, the difference between the mode of the distribution and the lowest probability value isn't that much. So this means that, especially in cases like this, where we sample a very limited amount from the distribution, so like at most 20 or 15 iterations, it's really prone to being dictated by just complete chance. Like, it might not be able to sample the good distributions often enough so that it gains good confidence on the models that are actually good enough. And so the score-based variant also has a problem that it's on the other side of the spectrum. It actually uses the value of the ELPD as a score that denotes the strength of a model. And as you can imagine, ELPD by itself isn't really meant to be used as a metric for identifying whether a model performs well or not. You can maybe perhaps use it to compare whether model A performs better than B, but then you can't take it and say that since a model has 10 times bigger ELPD value than another model, it's 10 times better. No, that just doesn't make sense. So a score based on purely on ELPD values, they're probably not going to work as a good indicator of measuring the strength of a model. And that's another portion that we need to work on, which is how we're gonna kind of bind the workflow topics to the model network. So, okay, we have a way to like describe a network of models, and then we do have a bit of some crude algorithms that can somewhat traverse around the model network wide enough to find some optimum under a given criteria. But then until now, we've only used ELPD, which just measures the predictive performance of models. But then there's many more aspects to Bayesian workflow, right? So we can like take into account like how well the posterior is possible to be faithfully computed, and like whether the model is interpretable or not. And so if we want to take these into account, like when we do Bayesian workflow, we kind of don't take a quantitative approach. We just use tools like simulation-based calibration and posterior predict checks to like kind of qualitatively analyze whether the model is sufficiently satisfiable. So in this case, how can we use like these tools that we frequently use in Bayesian workflow, bind them together to kind of aid us in navigating through networks of models? That's a question that I'd like to know the answer to. And this is also a bit more closely related to our algorithm design, but as of now, our experiments were mostly based on like numerical experiments. So what we did was we just came up with a couple of algorithms and then ran it against a couple of case studies to make sure that whether they have they worked as expected or our assumptions hold and etc. But then, to be honest, it's not rigorous enough. So if you want to make a algorithm that's kind of rigorous enough, we need to establish it based on theories. So, and then also provide like a performance bound, whether it converges or not. And then, so I recently read this really interesting paper about like finding whether a single covariate that's strewn across multiple models and how well this specific covariate contributes to the model's prediction. So it kind of takes that covariate and measures its performance across multiple models, and then kind of calculates a metric which describes how important the covariate is. And then the novelty of that was it provides like a theoretical bound of the metric, like so how much that importance metric is accurate enough. And then again, if we can somehow also try a similar thing and try to somehow derive a probabilistic bound of our algorithm that works in our model network, that would be a great way to kind of investigate more into how our algorithms behave in detail. And finally, this is a part that I'm personally interested in, but I think semantics has a really great relationship to modular stan, because if you take a look at modular stan, signatures and implementations actually contain much more than just code, right? Because when you write a modular stan program, if you've written one, then you kind of like separate signatures into like model constructs. So you would create a signature that denote the type of prior that you give to a specific parameter, or you can say, or you can write another signature that denotes the type of link function that you use, and so on. So what these signatures encompass is that they encompass the semantic construct of the model. And it's definitely there. It's there because we actually keep that in mind when we actually write the models. We don't suddenly like write a logic link to a prior of a parameter. We just only give distributions that can be used as a prior for a parameter. So if you think about that, one of the goals might be to finding the semantic field of a signature. So what a signature actually implies in the context of a model. And then, so for example, if you can identify that some signature denotes a prior for a parameter, or it denotes like whether a covariate is included or not, we might be able to find other implementations that is within the field or within the scope of the semantic field, and then perhaps automatically generate or kind of tune them to be more suitable to the semantic field. So what the signature actually implies, and that might help in automatically expand the network of models without having to manually write out the implementations yourselves. And yeah, to summarize what I just said, I kind of want to know whether we can learn what the model we're trying to describe is, apart from just trying to describe how to draw samples from a given model. And I think this might be very closely related to how modular STAN kind of describes STAN programs in really semantically segmented portions of code. And finally, there's also opportunity to really dive deeper into like interactions between implementations. Like I said before, like the multiple combinations of implementations. So like you can say some combination of a link function and likelihood works better and not. And we know that because of our statistical knowledge. And then what if we can kind of link together bundles of implementations? And then we can kind of use them to learn how models that possess that bundle of implementations behave. So I recently came across a paper that was linked in the STAN Slack a couple days ago. And it was about using paths in the abstract syntax tree of a STAN program to identify like whether if two STAN programs kind of shared a similar path in the abstract syntax tree, that can be used as a feature to potentially train a model that can predict the behavior of the model whether it converges or not. So we can kind of use multiple combinations of implementations as potential features that we can use to train and find common traits that are being shared between models that have that type of implementation. So I think implementations really give us perhaps a new tool to think about like whether we can semantically separate STAN models and identify the real abstract mathematical model that's lying within the realization, the probabilistic program. Yeah, so this concludes our presentation on our winter internship. Thanks all for coming and listening.
Good job.
Yeah, it was really informative.
Glad it helped.
Maybe any questions or feedback? Especially, I wish to get feedback from Aki and Ben and Ryan.
Oh, and I'd like to chime in that we kind of have a more detailed notebook that also has some details that we omitted for the sake of presentation. So I'm gonna link in the chat if you guys are interested.
I think it might be better to follow up the mail, the notification mail that I sent. Yeah.
Oh, sure. Okay.
Yeah, sure. But you can share through chat as well. Okay.
I can go first. I have a question about the algorithm that you guys have for when you compare two ELPD values. You gave a description sort of taking one of the sort of chunks of probability assigned to some models and transferring it over to the others. I'm curious, so I'm not sure I fully understood that section, and I'm curious how you guys arrived at that, because that's very interesting.
Okay. So if it might help you with understanding, we do have kind of like a pseudocode expression of the algorithm in the notebook, so you can look that up later. And so the basic, I guess, thought process was that if we evaluate ELPD for a single model, like that potentially might mean that we can also propagate the information to other models that perhaps might have some other similar traits of the model. And really, there's no exact way to figure out what that trait is, right? But then our reasoning is that given a sufficient amount of iterations, it should be enough to kind of, on average, find out which quote-unquote traits perform better in the scale of an ELPD. Would that answer your question?
Yeah, I think so. One comment I have is that I wonder if in both of the algorithms that you gave that use ELPD, if including uncertainty in the scores might help you to sort of converge better.
Yes.
Yeah.
That's a very, very good question. So what we did when experimenting is we actually pre-computed ELPD results of the entire model network, because realistically, it's going to take like hours to recompute ELPDs, right? And then that's actually has a problem in itself, because first, it doesn't take into account the stochasticity in regarding ELPD computation, what you mentioned. And because like subtle differences in ELPD can lead to like completely different results. Recall that we only checked for inequality. So if we already had two ELPD values that were very close to each other, and then we completely disregarded the randomness inherent in computing ELPD, it's never gonna give a chance for the ELPD that's smaller to kind of go back up, because it's locked in place. We don't take into account the uncertainty. So what you said is it's a really good question, because that's also a part that needs to be incorporated and take into account for. Yeah, and we kind of internally debated a lot on whether it's right to use like pre-computed ELPD multiple times, because even I think Yuling said that if you reuse ELPD, it's not going to be right, because there's like a lot of stochasticity involved in it. So good comment.
Hi. So can you share the slides again? So I can ask about the specific slides.
One moment. Okay. Here you go.
And also comment, don't ever use that kind of slide which has only thank you. It's much better to leave as a, because this is zero information slide. You can say thank you aloud, but if you show this, it's not useful for anyone. If you go one slide back, this is useful last slide. Leave this and then ask questions.
Okay.
And it's much easier now to remember what you wanted to say as the last thing.
Right.
Here you had many, many things, and people are preparing to ask something, and if you then switch to thank you, they forget what were your conclusions.
Yes, I believe it was a bit redundant.
Yeah, never use thank you slide.
Okay.
But go back. So this was a good slide, and then there was the this score-based.
Yes.
So now in the distributional, you said that you only compare it with inequality.
Yes.
But you could compare also ELPDs either with the probability that one is bigger than other, getting value between 0 to 1, or you could use this weighting, so difference exponentiated corresponding to these like Akaike weights. And that's another way to get value which is between 0 and 1.
Oh.
And so you could use those continuous values to more quickly see which models are clearly better than the others. Now in these experiments, you had a quite small number of models, and the chain approach it's
yes.
Of course great that you really are benefiting from the certain structure. And then if you don't have that, like the chain approach would not be useful, because you have models that are not easily ordered. There's specifically in that case, it's more likely that you would see overfitting when you are comparing many models.
So in
and
the sense
like,
of the probability?
So because this ELPD is estimated and it's there's some uncertainty in that and variation. For example, if we add additional covariates, but that covariate is completely irrelevant, it is still possible that just by chance it looks like it helps. And it holds also for cross-validation, that even if the cross-validation gives you unbiased estimate of the predictive performance for a single model, when you compare two models or more models, after the selection, the cross-validation estimate is not anymore unbiased, and it's actually likely that the model which had higher, so if the cross-validation estimates are quite close to each other, and if you then choose the one which did get better estimates, it's actually likely that you are selecting the worst model, and because you are selecting the one which just by chance looks like better. And so this is illustrated, for example, in our Viron and Vehtari paper in case of variable selection. Of course, there we have much larger number of models, so it's more likely to happen. So
Yeah, I think that's a very significant issue, and yeah, definitely it's gonna impact, especially if you scale it up to much bigger models. That's complicated.
So I'll put it in chat just in case. So this paper has these examples of severe overfitting when using just ELPD score.
Sorry, Aki, just so I understand, if you're saying that you're actively selecting the worst model if you're selecting the better ELPD score between two, I guess I don't. So I see how it could be misleading.
Yeah, so in the case, so if you think about a model and then another model which includes just one irrelevant covariate, completely irrelevant, it should not improve the performance.
Mm-hmm.
But it is possible that with finite data, just by chance, it can look like that it's improving the prediction.
Mm-hmm.
And it can also, in case of cross-validation, it can just by chance be such that also the cross-validation estimate is a bit higher.
Is it possible to compensate for it?
And then in this case, so when we know that it is really completely irrelevant, and then if we did, if it looks like that it is based on cross-validation helping, it means also that we did estimate the coefficient such that the coefficient, the posterior can overlap 0, but it's like the posterior mean of that coefficient is not close enough to 0, so it is really having influence. And then if you would compare then with the independent infinite sized test data, you would see that actually your performance dropped. Of course, in such case, when you are adding a covariate that is actually relevant, and it's so much relevant that the performance is much better, then adding that, like the selecting the better model really gives you better model. So the problem is only when we are comparing many models that have very similar performance. That in such cases, you can think of that we have the ELPD estimate, and there's some variation around it, which depends on specifics of like which covariates we are including or what kind of model structure we have, and so on. and just by chance some model combination, then the can look better or can look worse. And so when we are comparing models where so we can, for the ELPD difference, we can compute also for that the uncertainty, like the standard error. If there it looks like that, based on that standard error, we can't decide which model is better. We should not choose either. And this gets worse when we have many models. And in case of variable selection, it's common that either we have their irrelevant variables or we have their correlating relevant variables, but so that if we've already included some variables, those additional variables don't help. And then because of combinatorics, we can have like millions or billions of models to be compared. And then in each selection even the small selection bias, it gets amplified when we have many models.
That makes sense. Thank you.
And then this is, of course, also amplified when we have small data, because there's more uncertainty. It's more likely that just by chance something looks like relevant. When we get, like in variable selection, when we get more and more data, even for the irrelevant covariates, even if the cross-validation would pick those irrelevant ones, if we have big data, the posterior of those coefficients gets close to 0, and including them is harming you, but it's harming you so little that it's not a problem.
I'd imagine it like to be a problem when you're kind of comparing models that are good enough. So when you have a couple of really relatively well-performing models, and the performance difference between them is like really minuscule enough such that, you know, just random irrelevant covariates can really affect it due to just pure chance.
But then, so one thing that like using this optimizing ELPD score, I think it's fine when we have small number of models, and if the best model is clearly better than the others.
Mm-hmm.
Otherwise, then this projection predictive approach would be better. In the projection predictive approach, we are currently using forward search, but then it would be possible to then look for these faster searches there too. And so the in variable selection, and in also when looking at the hierarchical models, currently we do it with forward search, and then that forward search can be also slow because of there's still so many possible models for the next step. There can be also sometimes cases that the forward search is not optimal. There are also cases where we might like to make the search first with slightly faster computational approach and then refine. So in the projection predictive approach, one thing which affects the cost is how many posterior draws we are projecting. And then if we project less, the search is faster, but gives worse results. And then if we use more, project more draws during the search, it's slower, but we get better results. But could we then kind of combine this, that we start with the faster search and use that to give better guesses that which model combinations to check more carefully. And so this is related to this, like trying to estimate probabilities of how good certain models might be, which models still to check. In addition of forward search, we have been using, specifically for the variable selection, we can use also lasso type L1 search, which we've noticed that it also gives worse results, but it's much faster, so it could be again used to initialize better search.
Aki, is there somewhere that
and
we
all
can...
the time with this projection predictive approach, it's much safer, even if we have a very large number of models.
Is there somewhere that we can read about these different approaches to search with projection prediction? Have you published anything?
So they are mentioned in so we don't have in these publications, there are not very detailed experiments reported. So we have done a lot of experiments. So we've used forward search and backward search and L1 search, and with different of these variable selection complexities, different sample sizes, and different number of covariates and so on. But then only reported so here so in chat, so section 4 is search strategies. And so we mentioned there forward search and then this L1 search.
Maybe I can ask about this offline. Sorry, I don't want to derail the questions about the presentation.
And then so in a way like this like so there's a real need for making this projection predictive variable selection faster, and in those cases we have huge number of models, and then if that can be made faster, then it can be also then generalized to other types of model structures. And I think I would start with the running L1 search and using that as the initial guess of making guesses which other model combinations to start searching, and then these the ideas in this presentation would be useful.
Right, so L1 would be particularly useful in situations where you can give each of the program components a numerical contribution, so that they have coefficients.
So the L1 is
you need a coefficient.
L1 is specific for variable selection.
Right. Okay.
Thanks for your comment. I think I thought more about ELPD during this short time frame than during the entire winter. And it gives me a lot of food for thought.
I have another question if no one else wants to go. So it seems like, at least for the score-based algorithm, you have in your mind some probabilistic model of how implementations affect the quality of a model. Does that make sense? So I think you mentioned that the scores for implementations are summed in order to estimate the score for a model that is made up of those implementations. I'm wondering if you ever made that into an explicit probabilistic model, because it sounds kind of like the foundation of a regression problem.
Tang, should I answer it, or would you like to answer?
You can first answer, and I'll add to your answer.
Okay. So first, we take the sum of the model, the ELPD scores that contain the implementation, and then we take the average of it, not just the sum. So it just kind of more denotes like the average performance that is in terms of ELPD that a specific implementation has. And can you like elaborate a bit more on like the regression problem and how you view it as one?
Yeah, so the relation I see is that in regression you have sort of a dependent variable, and maybe we can think of the dependent variable as being the quality of the model and the independent variables being the qualities of each of the implementations. And then you also maybe have an uncertainty term. But you can also view each of those contributions as random variables themselves. So maybe that would help you include the uncertainties in each of the implementation scores. But
so
could,
I guess
yeah,
what you're saying is like we can view like the quote unquote scores of the signatures as like how big, for example, the coefficient, the regression coefficient is, and then on top of that you add another term that takes into account like the uncertainty regarding the model. Is that correct?
Yeah, that's right. Yeah, so you're trying to learn,
sense, right?
You're trying to learn the regression coefficients on each of the model or sorry, implementation contributions. Yeah,
I think that's a really interesting way to look at it.
And then regression, I guess that would be a linear regression. I think you could make it more sophisticated if you wanted to as well. For example, you could have a term that adjusts for the combination of any implementations. So just like in a linear regression, you can add features for combinations of features. You could do that here as well.
Makes sense. Yeah.
But it seems like this is kind of, yeah, go ahead, Aki.
That's my connection dropped out for like almost 2 minutes, so I might have missed something. But there's also stand gathering starting in 2 minutes. So is there any final questions?
I think I'm fine with the questions I think I learned, and it really gave me a lot of stuff to think about. So
okay,
my brain's gonna blow up if I ask more questions probably.
Actually, I have one question. If we want to get feedback from student community, which method do you recommend? Do you want, like, for instance, presenting this shortly after the STAN meeting?
So say again.
If we want to get feedback from general STAN community, which method do you recommend?
No, I didn't understand the question.
we want a community feedback because this is related to workflow. And Shin has also made a notebook. So if we want to get a direct feedback between posting on a discourse or, for instance, presenting shortly after the stand meeting, which method do you recommend?
I don't know. Also, I think that they were a bit, at the moment in this presentation, there were like some unclear issues. So it's not necessarily yet time to ask wider feedback.
I see.
So I recommend to think a bit more of this.
Yeah, because Ryan and I was planning for kind of a like workflow paper or big paper where from the computational language and all this choosing or prediction and also to the optimization part is included. Yeah, so I want to get like a timely feedback on whether this is along the trend and like, what people really need.
Yeah, I think it's just that now I don't think that this presentation was yet clear enough. And also there's a difference between what people think they need and what they actually what would be beneficial for them. So
okay.
But okay, I'll switch now to the stand gathering.
Okay. Yep.
So thanks for the presentation.
You. Thank you very much to you both.
Thank you.
Let's keep in touch.
I guess isn't any more questions to have. Maybe you can end it here.
Actually, I have some. Can I ask you some question?
Of course.
First of all, thank you for the great presentation. It was really informative. Actually, I have two. The first one is when creating the probability, do you assign or just randomly like uniform distribution?
So when we initialize the search?
Yeah.
Yes, we start with the uniform distribution.
So is it you assign the probability or it's just randomly use the uniform?
Yeah, we would have a vector of probabilities that sums to 1, and then initially it would be assigned to the uniform.
Oh, I see. Thank you. And also, can you go to the graph slide?
This one?
Yeah, I was just wondering which one is regarded as a good one? Just like showing trends or randomness or convergence?
So the y-axis denotes the evaluation metric that we use to check whether a model performs well. So if under perfect circumstances, a model that has a high ELPD score should also have a somewhat high probability assigned to it, and vice versa.
Okay, and for the right one?
Okay, so this one is a bit harder to interpret because there's no answer. This just shows like if we look at the x-axis as the domain of models, then this shows the actual probability assigned to each model.
Oh, I see.
Yeah, this denotes the index of the models of the network.
Okay. Thank you very much.